Hello everyone, welcome to Cracked Coding, and this is basically a new series that I'm going to be starting where essentially I am going to be helping all my friends get jobs as software engineers, and I'm basically going to be making these videos to help them prep for the interviews. This video is going to be around system design interviewing, a really common interview for a lot of these software engineering roles. But yeah, in this video, I'm just going to be going over the basics of system design. Just two parts of this video. The first one being key points I really want to highlight when you are doing system design interviews. Notable points just to keep in mind. You probably already know these, but I just want to reiterate them and stress them because they're very important. And the second thing I'm going to be going over is the interview steps. So system design is very abstract in nature. And one thing that really helps is coming into the interview with like a predefined plan. Obviously, you want to still be very flexible, kind of going with the interviewer, seeing how the flow of the conversation goes. But it really helps to have a backbone at the back of your head. And these are steps that I specifically follow. They may not necessarily be what you like, or there's no right steps, but this is what I feel the most comfortable with, which is why I'm going to be sharing it. So just take that with a grain of salt. But yeah, the first thing I want to say about this video is before you even get started, I highly recommend that you have some basics of system design before getting into this video. Otherwise, it may not be as meaningful. Some of the content I'm talking about might not make as much sense. So by that, a couple sources. The first one is the Alex Hugh Volume 1 book. I think this is like a really good book to just get started with system design, especially for a mid-level role. And I would say, at least for this video, you just need to read the first 5 chapters. The more the better, but definitely just having the fundamental knowledge for system design is pretty important. Another resource is Nico's system design video. Shout out Nico. If you're watching this, please like and subscribe. I love you. But anyways, he has a course. It's in his premium. He has a really good course. I can pull it up. Let's see. Yeah, it's like, I think it's this one right here. Yeah, as you can see, yeah, I already watched the majority of it. But yeah, I think this course is really good. But obviously, you have to be a pro member. I mean, this is a really, really useful website, so I even recommend subscribing to that. But yeah, and if you don't have access to that, it's fine. You have this book. I think you can find online, maybe legally. I don't really know, but yeah. System Design Primer is the final resource. It's like a pretty common, pretty popular GitHub link. Yeah, it's right here. It's another free resource. A lot of prep material, as you can see. Yeah, this goes into a lot of detail, and I definitely recommend if you have time to read all this. But yeah, any one of these definitely works. But yeah, I just want to say that real quickly. Okay, I actually already recorded this video before, and the file was kind of shit, so I'm re-recording it. So I have all my notes written out. Like beforehand, I was writing it as I was recording it, but it'll just make it a little easier and probably a little faster. But okay, the first thing is general notes with system design. There's no correct answer. Yeah, I really want to highlight this because I feel like this, at least when I'm in an interview and I'm like really nervous, me reminding me of this helps calm me down. Because there really is no right answer. Like one problem could be solved in like 5, 6, 7, 8 different ways, maybe more. There's no specific unique solution versus like LeetCode style interviewing. Usually they're looking for a specific algorithm. Sometimes you can use multiple algorithms, but most of the time it's like a specific algorithm they're looking for. System design is very different from that, which is why it's really important to remember that it doesn't matter like what you're saying. It's not about what you're saying is the right answer. It's more about like your reasoning for why you're suggesting one thing or the other. So even if you're designing a system and as you're designing it, you realize that there is actually a flaw in your design, just talking about what that flaw is and how you can mitigate that flaw you're still in good shape. If you're able to talk about that both of those things, I think that's really good. So that's why I feel like it definitely takes some pressure off when you're solving these type of questions, knowing that there's no right answer. You can always be flexible as long as you give a valid reason as to why you're designing it in one way. That's all that really matters. Next thing is just the primary goals. So on a high level with system design, actually. Give me one sec. I'm just gonna hide all these. Anyway, so your primary goal when you're doing system design is you are trying to focus on these three elements. You want it to be highly available, highly reliable, and also very scalable. So these might sound like the same thing, but essentially what they mean is availability is how available is your system. So if you have like a website, how available is it so that if a customer goes to the website, that website is up and running? Versus reliability is more so like in an event that there's like a crash or a sudden partition, how does your system handle that? Like, do your databases have replicas? Do you have like a second load balancer, etc.? How are you able to mitigate the damage from just there being like a single crash or a point of failure? That's the difference between availability and reliability. But essentially you want your system to be able to have both of those. I think those are really strong things you want to focus on in your design. Lastly, the main obvious one is making it very scalable. With every system design, you're designing something that is taking in a lot of traffic, and you want to make sure that your design is very scalable. And the last general note I want to talk about is fundamental requirements. I think this is a really slept on concept, but in my opinion, it's really important at the beginning of your problem to clearly establish your fundamental requirements, because the rest of your solution is all reliant on those fundamental requirements. Essentially, those requirements dictate the flow. So when you're going into like your non-functional requirements, your API design, your storage and databases, all of those are going to be connecting back to your functional requirements. So you really want to make sure that you fully understand what the functional requirements are before solving the problem, and make sure you ask all the clarifying questions you need to ask for you to fully understand that. At the end of the day, you don't want to be solving the wrong problem. That's happened to me in practice. So yeah, that's something really important. Okay, so the next thing I want to talk about is CAP theorem. If you're not familiar with this, I highly recommend that you look this up and fully understand it. Just a note, anything in red are just like terminologies that I just want to highlight that you should really know. So in case like you see something in red that you're quite unfamiliar with, definitely after this video, look it up online and get really familiarized with it. But yeah, so CAP theorem, essentially, just to keep it really brief, if there's like a partition, you have to either prioritize consistency or availability. Obviously, in any system, you really want to have both high consistency and high availability. But at the end of the day, not every system is perfect, and you're going to hit a threshold where you have to pick between prioritizing one or the other. To give you an example of what exactly this looks like, let's take like this employee database example. So let's say we have like an employee database, just has data on like employees, and we could say that we have 3 database replicas. So the same data is stored on 3 different databases. In this example, prioritizing consistency means that anytime a user is querying the database, they're most likely going to get the most accurate data in the databases. So let's say like a user makes a change to a database, to one of their data points in the database, and then someone else is trying to read that data. If we prioritize consistency, the person reading the data will more likely get the latest data that they're supposed to get. Versus with availability, rather than they may not get the right data, like they might get old data, but anytime they're trying to read data from the system, they're always going to get data back. So there won't be there will be less instances where, who knows, maybe the databases are not working and they just don't get any data back. So in this example, usually availability is prioritized over consistency, because the downside with consistency, as you can see, is it doesn't really account for the downside with consistency. Sorry, let me repeat that. The downside with consistency is if the website is down, no one's going to be able to access the data. And that is more detrimental than the data being consistent. A lot of these use cases, it's okay for the data to be eventual consistent, which is what I have down here. And we can usually have high availability. So that's one thing I wanted to talk about, was in most problems, it's usually just going to be, you're going to be prioritizing availability over consistency. The only two problems I've seen where consistency is favored over availability is, one, Google Drive, because with Google Drive, it's really important that, especially when like people are editing the document at the same time, sometimes it could get weird if people are editing the same sections and you don't have the latest updates. So consistency helps in that sense. And furthermore, if there is a partition and you lose connection, you can still be editing the document offline, and once you reconnect, then you can sync your changes. And the other example is banking, because with financial data, it's really important to be consistent. Let's say you're transferring, like you're trying to withdraw money, but your bank account was not updated with the latest transactions. It should actually be at $50, but it's actually at $100, and then you withdraw $70. That's really bad, because all of a sudden you're withdrawing more money than your bank account should actually have, and that can get really tricky with money. So that is another example where consistency is very favored. But in most problems, availability is usually prioritized over consistency. And one last thing I want to say is, these two concepts they're not tied down to the entire scope of the problem. What I mean by that is, when you're answering a problem, some elements some of your functional requirements, you may want to be prioritizing availability. In some other functional requirements, you may want to be prioritizing consistency. So this is not a binary choice for your problem. It differs based off of the functional requirements. You could have a situation where for all your functional requirements, you want to prioritize availability, but just want to keep that in mind, that you can also very easily have availability in part of your requirements and then consistency in another part of your requirements. And that will be more apparent as we get into the interview steps, but something I just wanted to say. Alright, so the next thing I want to talk about is NoSQL versus SQL. So yeah, this is a pretty important concept. More than likely, you're going to be asked for your storage system and your databases in your system, what type of database do you want to use? Very similar to what I just said with CAP theorem, your system could have multiple databases. Some of them you may want them to be NoSQL, and some of them you may want them to be SQL. This is also not a binary answer. But yeah, anyways, in choosing the database, I kind of break them down to different tiers. Tier A, I feel, are more impactful to your decision making. Tier B is also important, but not as impactful as the points in Tier A. So in Tier A, the first one I want to talk about is ACID properties. As you can see, I highlighted that in red, so definitely understand that if you're not familiar with it. But just a quick overview, ACID is specific to SQL, and what it stands for is atomic, consistent, isolated, durable. This is what makes SQL powerful. They're very durable. If there's a query that's being done on the database, it will either be completed in full or it won't be completed at all. Like, let's say like you're withdrawing money from one bank account and then transferring it into another account. You won't have a situation, if it's a SQL database, you won't have a situation where it withdraws the money and then there's like a crash and that query does not happen at all. Like, it will not do it at all, or it will fully do the entire query. And that's what makes SQL really powerful. The reason why I put this in tier A is because you want to think about your database and the situation and see if ACID properties are actually going to be having an impact on what you're trying to accomplish. If it is, then you might want to slightly lean for SQL. But if ACID's not really benefiting your situation, you may not really need to use SQL. You could rely maybe on NoSQL, because at the end of the day, SQL does have some downsides. One of the main downsides being that it's really hard to scale horizontally, especially when you're starting to get into data that is quite large in size. SQL is very inefficient in indexing when the database contains a lot of indexes. So just something to keep in mind. And that brings me to my next point. Perfect transition. Size of your data. So your size of the data also is pretty impactful. I'm sure you guys are familiar with back of the envelope calculations in system design, but this is where it would be important to do a back of envelope calculation for your storage in your system. And based on the size of your data, you can kind of assess what database you want to use. For example, like let's say like you calculate all the data in your system and you realize it's only 50 GB of data. That's honestly not a lot, and in most situations you can always make a case for SQL just by this size, because it's really not a lot of data. Versus if something's like 100 terabytes, that is definitely a lot more data, and it could get really complicated trying to partition or replicate a SQL database. So you could make a case for NoSQL with this amount of data. We'll get into general benchmarks later on, like what is considered a lot of data, what is not considered a lot of data. I'll get into that later, but yeah, just one thing I want to point out is basically, in summary, the size of your data does have a pretty big impact on whether you're picking NoSQL or SQL. Tier B. Okay, these are not as impactful. The first one being relationships and tables. Obviously, SQL is really powerful when you're working with highly relational data. However, I wouldn't say that's like a deciding factor. Like if I have data that's like super relational, but like it's like a petabyte, I might still consider using a NoSQL database. But just something to keep in mind. Second is also structured versus unstructured data. If you have structured data, that's better for SQL. If you have unstructured data, that's better for NoSQL, like more specifically like a document database like MongoDB. Alright, and the last point I want to talk about is read to write ratio. So read to write ratio. So this is not as impactful, I would say, in deciding between NoSQL versus SQL. It's just something I just wanted to list out because this is something you should talk about in your interview. So just to reiterate my point, read to write ratio does not help you decide if you're picking NoSQL versus SQL, but what it will do is it will really help in later parts of your solution. So when you're drawing out your solution in the high level design, maybe you have a lot of writes and you want to incorporate more leaders in your leader follower pattern, etc. It could be your ratio could help determine other things along as you go through your interview. But one thing I do want to say is, let's say you do and decide to go with like a NoSQL database. If your read to write ratio is has a lot more writes than on average, then you might want to consider using like a column-wide document, or what is it, column-wide DB, like Cassandra. Cassandra is like a NoSQL database that is prioritized for high writes. Versus if you just have like a lot of reads, not necessarily a lot of writes, you could use something like DynamoDB or even MongoDB. But yeah, and yeah, that's just something. Yeah, Cassandra is really good for high writes. I believe it's because Cassandra has some sort of cache where you can where I think the data is written into the cache first, and then later on it is transferred from the cache into your actual database. But the fact that it's being written to the cache makes it that the writes are much quicker initially. That's what I think. But yeah, if you're interested, definitely look that up to verify that. Okay, I'm going to give some actual examples of some databases. Honestly, this is not a requirement, but I feel like being knowledgeable on specific examples of database is a really it's something. If you can do it, I definitely think it's just extra brownie points. It looks good. It shows that you're very knowledgeable about current technologies, and definitely something I would consider just learning. Doesn't hurt, and it's not a lot of information anyways. But so for SQL, the main one you're really going to use is AWS RDS. I mean, I'm sure there's also like Azure counterparts, or maybe even like Google Cloud counterparts, but yeah, I don't really know those. I think just knowing the AWS ones is fine. But yeah, so AWS RDS, a pretty popular one for SQL databases. As for NoSQL, for a key value database, you can use DynamoDB. For your document database, you can use MongoDB wide column database, which I said earlier, but high writes. You can use Cassandra, GraphDB. This database doesn't really come up that often. And you can use Neo4j. You don't have to remember that. I don't think I've like. I'm pretty sure I looked this up online. So yeah. Anyways, these three are like the more common ones up here, and then also blob storage. This is really common too. Essentially, if you're not familiar with blob storage, I'm gonna put this in red. But blob storage is commonly used to store large files, so like images, videos, log files, etc. It's pretty obvious when something requires blob storage because it's not like metadata, it's like actual data, like videos or images. And typically you could just say you're going to be using S3. Yeah, and then one small thing I just noted here was like, I thought this was also kind of important, but like, if your use case involves long tail data, then usually you want to use a key value database. If you're unfamiliar with long tail data, what long tail data means is, think about logs. So logs are a type of data that you just always want to have historical information stored somewhere, but at the end of the day, you're most likely only going to be reading the most recent logs. Like rarely you're going to be looking at a log like a year ago, maybe like 2 years ago, or maybe on like a specific date. You're rarely going to be looking at that data frequently, but you're mostly going to be prioritizing the most recent data. So in this situation, you can say that of all the data, 10% of the data is what the user is frequently accessing. 90% of the data is just there, but not as frequent. In this example, that 10% is quote unquote the tail, which is what is long tail data. I think that's what the tail means. I actually don't know exactly, but essentially what long tail means is basically only like a use case where you're only using like 10% of the data and you're not really using most of the data majority of the time. Alright, so next thing I want to talk about is back of the envelope calculations. Yeah. So these, I would say that, so you don't have to do back of the envelope calculations. Like, honestly, if you're not really good at doing math quickly on the spot, that's perfectly fine. You can kind of skip this. I mean, ask your interviewer, like, you can be like, hey, like, are you interested in seeing any back of the envelope calculations? And they say you can pass, and you can pass. I personally like doing it because I got really comfortable at doing the math on the spot really quickly. And one thing it shows your interviewer is when you do these like math calculations and then you get a number and you make a decision based off of that number, it shows that you make data-driven decisions, which I think is a really good skill to be showing in an interview, especially with limited data. So I personally like doing it. However, I do want to say it's not necessary. And one thing also with this is when you're doing these calculations, there's only two main types of calculations you're really doing. Third is optional. The first one is queries per second, so seeing how many queries your system is taking per second. The second is storage, how much storage your system will be requiring. And this is really optional. The last one is bandwidth. It's not really applicable to a lot of scenarios. For example, I would say it's applicable to like YouTube or Netflix, where it's a streaming service. You're going to be sending video data, which is high bandwidth. That's like a scenario where you would want to calculate this. But like if it's not a service where there's high data that's being transmitted, or I should say large amount of data that's being transmitted, then you don't really need to do this. That's why I put it as optional. So just some general benchmarks when it comes to these. Starting with queries per second, these numbers are like something you get more comfortable with as you are doing more problems. But in my opinion, 100 queries per second, it's really not a lot. If your system's getting like something in the hundreds, that means your system it's very manageable. Hundreds, it's really not a lot of queries. 1,000 to like 10k, that's a decent amount, but it's still manageable. It's not like an insane amount. And then if you get to like 100k plus queries, that's like a shitload. Definitely think about it in your system design. I think when I was doing like Tinder, I calculated to be around 100,000, and I was like, wow, this is quite a bit. Okay, moving on to storage. Similar thing, 10 to 100 GBs. It's not a lot. Very manageable. You could definitely get away with SQL with this. 1 to 100 terabytes is a decent amount. I would say with this, like, you can either still pick between SQL or no SQL. Like, you can still do SQL and partition it, but yeah, this is definitely more a decent amount. And then if you get to like the petabytes, this is definitely a lot of data. No SQL, or maybe even an S3 bucket. Usually when you get to petabytes of data, it's usually because maybe you're designing Instagram and you are trying to store your images. So yeah, that would usually go in a S3 bucket. Okay, and down here is basically a table that I have that's just useful to have. Basically, like, just saying like a kilobyte is 1,000, megabyte is 1,000,000, etc. And I also wrote it out in exponential form down here. When I do like the envelope calculations, I like to break everything down into exponents, and that makes it a lot easier to do the math really quickly. So yeah, this table and this right here is something I like to refer to. And the last thing is just this nifty table of general storage amounts for different types of data that you might run to in a problem. So like one character is 1 byte. So a string for like a search query, you can assume like on average it'll be like 20 characters. You can say this is 20 bytes. This is useful for like if you're like trying to design an autocomplete system, something like Google, where it like when you're typing something in the search bar, it autocompletes a bunch, like it shows like the top results. This is something like, this is like an example for that sort of problem. A URL, you can say it's like 500 bytes, which might seem like a lot. It's better to be over than under, and a URL sometimes has like a lot of different parameters, offset limits, etc. LeetCode contest, this is very specific to a problem. 10 KB web page size, 500 KB, etc. for like images, videos, etc. Yeah, and you don't have to be these are not exact values. Like you can say an image is 10 megabytes. You can say a file size is like 50 kilobytes. None of these are exact. These are just approximations. And at the end of the day, if you don't know what to approximate for like an image, it's okay to ask the interviewer. Just ask them, hey, like, what do you recommend I should be estimating the storage amount should be for an image. Okay. Yeah, okay, so before we get into the last section, let's go Excalidraw. Yeah, so just the general structure of how a system design looks. Usually you have like a client, and the client is going to be setting a request to a load balancer. Let's switch this to one arrowhead. Also, one thing to note is these are just like this is like a library I downloaded from the internet. I prefer this over like using the default ones because this could like take a lot of time. Like let's say like, okay, one thing that's really nice about this is, so we have like this that we're calling like a server. Obviously with any like in any system you want to have multiple servers. So the nice thing about this is that it has like 3 squares, which indicates that there are multiple instances, versus for this, you're gonna have to draw it out every single time, and it can be annoying. Yeah, so this just helps like save a little bit of time. You can save preloaded images, and especially if you're doing Excalidraw, then it makes it a lot easier on the interview. But anyway, so going back to the main thing, so yeah, so usually you have a client, a load balancer, and then usually you have like an API server, and this could be like your API gateway, just redirecting all your requests, and then you might have like, you'll have like service 1 and then service 2, and then this will be redirecting requests to those services like this. And then as well, you'll have like databases, different databases. I'm not going to get into super detail. You have like a cache, maybe for the databases, yada yada. But yeah, I mean, this is like the core feature in every system design, like all this right here. And then I would say this remaining section really changes based off of the problem. Okay, and the next thing I did want to talk about was message queues. So this was a concept, honestly, that took me quite a bit of time to understand initially, because I don't know, like, so message queues are really advantageous because they decouple the system. So when I first learned about message queues, I always try to implement message queues because I just assumed that decoupling the system was always the way to go. But definitely there are situations where message queues will help, and there's also a lot of situations where they may not actually be the best answer. But just yeah, look into message queues if you're not familiar with it. But in summary, like I said, message queues, how they work is they really they decouple the system, and how they work is essentially, let's say the server is sending a request to this message queue. That request will be sitting in this queue, and you'll have a bunch of workers at the end of the queue who will be taking the requests and handling them one at a time. When they're done with the request, they'll come back to the queue, get another request, etc. This is really beneficial because like I was saying earlier, it really decouples the system. So let's say we have like the first part of the system, which is this blue dash box, and the second part of our system, which is this green dash box, and then a second system, which is this blue dash box right here. Okay, so let's say this service sends a request to the message queue. Let's say for some reason this green box, everything crashes and is no longer running. The good thing is, now that although this green, all these services crashed, our message is in the message queue, and we can still process this request regardless of what happens to anything here. This is what I mean by decoupling. The message queue and the workers are irrelevant to what happens all here. That is the power of message queues, because it's really easy to decouple the system, break like a monolith system into microservices. And yeah, this is really, really, really beneficial, especially when you're trying to scale your system. So I guess that brings me to the next question. How do you know when you should use a message queue and when you shouldn't use a message queue? One thing I like to think about is synchronous versus asynchronous. So when you're making a request, do you want your request to be synchronous, or do you want your request to be asynchronous? Synchronous means that you send a request and you're waiting for a response back, and then you eventually get a response back. That response usually contains data on the request, and you're good. So an example of this is just HTTP. Especially if you've done like API design for HTTP endpoints, you know that you're usually taking like a request, doing something with that request, and if necessary, you send a response back with data. Versus asynchronous is, rather than waiting for the response back, you just send that request and that's it. That request sends in the queue, it gets fulfilled. It might be successful, it might be a failure, you don't hear anything back. You could I'll get to this, but you could long pull for a notification regarding it. But anyways, that's what asynchronous base essentially means, is you just send a request, it sits in a queue, and that gets fulfilled on its own. So we'll talk about asynchronous first, because what are the benefits? Like I was talking about, so this is with the message queue, decouples the system. It's really efficient for scaling. And let's say you want a response back. One thing you can do is you could have like some sort of like notification service. Okay, notification service, and we can have it so our client is using some sort of long polling to just check this notification service consistently to see if there's a new update, and then anytime a worker fulfills a request, we could have it update the notification server as well, and then eventually the client will get notified about the update. So that's one workaround to getting response back. However, sometimes this is really this is kind of extra and inefficient, and it might just be simpler and better to just be using a generic synchronous request rather than using an asynchronous request. Sometimes like these long poll requests to the notification center services, maybe there's just like a bunch of wasted requests, like out of 1,000 requests only one is actually getting data, and maybe for our system that's really inefficient. But yeah, that brings me to the cons. So it's a lot more complex to implement, because you're gonna have to implement like a message queue, notification service, and also there's no immediate response. So then moving on to synchronous requests. The benefits with synchronous requests, which is essentially what we have in Service 1 and Service 2. Let's say you're just trying to you're trying to just pull data from your database, and sometimes that data might just be stored in cache. It's not worth putting that request in the message queue and then having your user pull a notification service. It's just easier to have them sit in an HTTP request, get the response back, and then deliver that to the client. So the pros are you get that immediate response, and it's very simple. The cons is it's very prone to crashing. So let's say like a user sends a request, and the request is taking a lot of time, and for some reason they get disconnected from the server. That request is now lost, and that's really in some systems that's very inefficient and very bad for the user experience. Furthermore, if there's a long wait time, that can also make the user more prone to crashes, and also having a long wait time is not good for the user experience. And the last thing is scalability. This makes it a lot more difficult to scale. It's definitely doable, but it might just be more expensive to scale. Okay, yeah, so that is the first part, and in the second part, I'll be going over the interview steps. Alright, so part 2 of this video. So now we're going to be going over the interview steps. Let me just hide all of these. And essentially, the interview is going to be broken down into 7 different steps that I like to follow. The first one is the problem exploration phase, where essentially you're just asking questions, trying to understand the problem, kind of what I was talking about before, but you really want to hone down on the functional requirements and make sure you're solving the correct question and that you fully understand the scope of the problem. The next thing is listing out the functional requirements, and these two can happen kind of together. Like you can ask some questions, list out some functional requirements, follow up with additional questions, either clarify your functional requirements or add to them, etc. Then it gets to non-functional requirements. These will be based off of your functional requirements, but we'll go over that. Then it goes to databases / storage and API design. So these two can be interchangeable. You could do API design first. I personally like doing database storage first, because in non-functional requirements, this is where I do my back of the envelope calculations, and after calculating storage, that's a really good transition into talking about the actual storage and databases I want to use. So that's why I like doing like this, but it's up to you. After these two, then you go to high level, and then after high level, it is into deep dive, bottlenecks, and pointing out single points of failure. Alright, so the first one, problem exploration. So the purpose of the problem exploration is you want to be asking clarifying questions to understand the scope, mainly because, like I was saying earlier, you want to make sure you're solving the right question. Some example questions are like, should I be taking into account authentication? Is it like US or global? What type of users are using this product? Honestly, I feel like these are just like example questions, but one thing I want to say, I feel like the questions are really important to like the scope of the question, for the scope of the problem, and these necessarily are not really focusing on the main these aren't really about like the main problem at hand. These are just like secondary questions, so take that into mind. Like, don't like, these are not the main questions you should be asking, but just some like ideas you can get. As for example, like for authentication, majority of the time you're not going to be taking into account authentication. I mean, it's good to ask this to show that you are thinking about that, but yeah, you're not really doing authentication most of the time in your design. But okay, let me talk about like a specific example of this. So one mock interview, the interview basically stated that I'm going to be designing a streaming service, and one follow-up question I asked was essentially, are the videos going to be uploaded to the service by like the service provider, or are the videos being uploaded by different users? In other words, I was asking, is a problem I'm going to be solving Netflix, or is a problem that I'm going to be solving YouTube? Those two have different functional requirements, and yeah, this is an example of a good question you want to be asking. And the interviewer told me afterwards that was a good question I asked, but you just want to be narrowing the problem, making sure that you're solving the correct problem. Okay, so like I was saying, these questions can be asked as you're listing functional requirements. It is not like it's a lot easier to be doing them in together. But once you come to functional requirements, one thing I like to do especially if it's a problem I'm really unfamiliar with, I like to write out the main players or the main stakeholders involved in the problem. And that really helps me kind of think about the different requirements. This might not be as applicable to like a really small scale problem like designing TinyURL. That's not like, there's only one user and there's not many requirements. But for something like DoorDash down here, which we'll get to, there's a lot of different players like the restaurants, the drivers, the customers. That's why for me it really helps me when I divide it based off of different users or players within the system, and then under each of those stakeholders listing out what requirements need to be fulfilled for those specific people. So through this entire process, I'm going to be using Ticketmaster as an example. We're going to be referring to this as I'm trying to explain some of my points. But in this example, I also did DoorDash and TinyURL, so we can go through all of them. So, for example, Ticketmaster. In Ticketmaster, there are three main players. Two actually, you could maybe do three. So I wrote out customers. So the customers are the people who are trying to like view the concerts, and for like a specific concerts, view the seats available, and then actually purchase the ticket. The artist, honestly, these should be separate. So viewing concert is one, and viewing seats is another. Artists, on the other hand, they want to be able to upload their concerts to the service. That is another requirement. And system, sometimes I like to put this, but this is not necessarily important. Essentially, this was like, basically, let's say like you have like the concert has like a general floor where there's no assigned seats. Basically, the system is in charge of keeping track of the number of tickets it's selling to the customer, just to make sure it doesn't go over capacity. But this could also just be implied with purchasing a ticket, like that's like the underlying logic. So you don't. That's why I put this in italics. Out of scope, we'll get to this later. But yeah, essentially breaking down by stakeholders. So going into DoorDash, the main players are the restaurant, the drivers, the customers, and the actual system. So restaurant being, if you're a restaurant owner, you want to be able to add your menu and all the details to your restaurant. Maybe perhaps update menu maybe you also want to design to have the ability for the restaurant owners to be able to update the menu anytime there's like a price change or new items are added to the menu, or even maybe some items are no longer available. Next thing is being a driver. So you want the driver to be able to like receive orders and directions. So essentially they're going to be given instructions of which restaurant they should go to pick up the food and where to deliver that food to. And then the customer is going to be placing the order, and then you'll also maybe want to include functionality to be able to track the driver's location. And then system, like I said, like system's sometimes optional, but like in this case, when the customer places an order, being able to fulfill the payment from the customer to the restaurant. Like I said, this could also be implied for placing order, like when the order is being placed, this all happens on the back end, so it's not really necessary. But yeah, something I just wanted to point out. And then going to tinyurl, this is very simple. There's only one use case, which is just like the users who use the system, and the only requirements are being able to generate a tinyurl, and then with that tinyurl being able to click tinyurl and get redirected to original website. Yeah, that's a little bit clearer. Okay. One thing I do also want to talk about is it's okay if you have a bunch of requirements. The one thing you do is you want to communicate with your interviewer to ask them which of these requirements you want to focus on. So the first part is a lot of requirements. Honestly, sometimes it's good. It shows that you're really thinking about the problem at a high level. You're really considering all the different requirements. And I feel like it's not a bad thing to have a lot of requirements, but one thing you do want to do if you have a lot of requirements is ask the interviewer of these requirements which of these would he or she want you to focus on. You can even give a recommendation. So like that's why I had Outscope here. Let's say it looked like this. I could perhaps be like, yeah, so for Ticketmaster, which of these requirements would you like me to focus on? I personally think in this design, the customer's requirements are more important to the system, and the artist's requirement could be out of scope, but just wanted to get your opinion to see where you wanted to take this problem. And yeah, the interviewer might agree with that, or if you don't even have to give a recommendation and you can just see what they say. But yeah. And last but not least, this is also a good idea to check with your interviewer to see if anything is missing. At the end of the day, you don't want to be solving the wrong problem, and just asking your interviewer if they have any questions or if there are any requirements that they want to consider in this problem. Usually they'll give you a green light unless you're missing something, and they might give you a hint, or they might even just tell you. Okay, so that is functional requirements. Now to non-functional requirements. So with non-functional requirements, you're going to be also asking clarifying questions, but these are going to be a little different. These are going to be on some assumptions you want to make in the system. For example, how many users, of these users, how many of them are active, so like daily active users. With our Ticketmaster example, like how many seats per concert, if that is relevant. On average, how many times does the user query the system? For Ticketmaster, we could say, for example, 5. This is going to be very similar to the questions up here, in a sense where you don't have to just think of all the questions on the spot. You can be listing out your requirements, and as you're listing them out or doing your back of the envelope calculations, you might think of additional questions which you can add. But yeah, this will happen in tangent with the remaining steps. Which brings me into my second point. Now you're going to talk about the requirements. So in general, usually you're going to be talking about the availability, the consistency, latency, scalability, and optionally either security or concurrency if those are relative to the system. Starting with availability and consistency, we already talked about this in the first part, but yeah, in general, you want to say that you want high availability and you want high consistency. However, you will also have to acknowledge that eventually you're going to have to prioritize one or the other, and then you can be like, for this system, I would like to prioritize availability over consistency, blah, blah, blah. Actually, I did make a mistake. You don't say for the system. Like I was saying earlier, these are going to be referring to your specific functional requirements. So you don't want a very easy noob trap is saying your entire system is available or your entire system is consistent, I like to relate these to specific functional requirements. So for example, in this, let's going back to this Ticketmaster example up here, viewing concerts and viewing seats, for those requirements, I would say we would want to prioritize availability. For the actual purchasing of the ticket, that requirement, we would want to prioritize consistency, because that's actually involving a money transaction, and we want to make sure that any financial transaction is very consistent and there's no issues or errors with that. Another example, low latency. So in this example, latency means the user's response. So like if a user is querying the database for concerts or seats, how fast they're able to get that information. In general, you want to keep it low. You want to keep the latency low in your system, and you just basically say that. But like I said, this is also not relevant to everything. So like for example, uploading concerts to the service. This is all happening in the back end. You don't really care about latency for that. Versus low latency is more important for the user experience when they're viewing concert seats, tickets, or even purchasing the tickets. Scalability for high traffic. This is a very general statement. You can always say, like, yeah, I want to make sure that my system is scalable for high traffic. Extra brownie points is a very easy thing to say. And then the last two, security and concurrency. So security, every system you want to have high security. That's without a doubt. However, a lot of the time in the system design, you're not really going to be thinking about authorization or security, unless maybe you're like designing like a bank where security is pretty important to the design. But like for example, for Ticketmaster, I mean, it is important, but Ticketmaster is more about the users buying the concerts, tickets, viewing the concert tickets, etc. The system design problem is not really focused around security. So usually, like, I don't mention security if it's not really applicable to the functional requirements. I mean, you could say it and just not write it down, just to show that you are acknowledging it, but I would say it's not always applicable unless it is kind of implied in your functional requirements. And the same thing as concurrency. So concurrency is not always going to be applicable. What does concurrency mean? So I use Ticketmaster because Ticketmaster actually involves concurrency. So concurrency means if two users are trying to purchase the same ticket, how is your system going to be handling concurrent transactions? You don't give the solution up front, but in the non-functional requirements, you're going to be saying, I want to make sure the system is going to be designed to handle concurrent transactions. And then when you go into the deep dive section, you can talk about different strategies. But for now, what I was trying to say is concurrency is not always applicable to the problem you're solving, but you want to think about it and see if there's any if concurrency is impacting your system, and if it is, you want to acknowledge that here. And then the last part of non-functional requirements is the envelope calculations that we were talking about in part 1, essentially queries per second, storage, and then optionally bandwidth. Alright, so now we go into the fourth part. When you're thinking about databases and storage, you want to, sometimes if you're confused, think about like your functional requirements and think about what type of queries are being made in your system, and essentially that will help you hopefully get a better idea of what type of tables or databases you need in your system. Once you have a better idea, then you can get to the next part. I like to list out the different databases and tables that are involved in the system. So for Ticketmaster, for example, we'll have like user data, concert data, ticket purchase data. We'll get back to this Instagram example later, but yeah, so for this Ticketmaster, we will have like these 3 examples of data. The user data is basically like when the user logs in, all that information stayed there. Concert data, this is data that's added on the back end for different concerts and all the seats available for this concert. And ticket purchasing data is like anytime a user makes a purchase, this table or database will be saving that information. So after you write out your different databases or tables in your system, then it comes to the read to write ratio. So like I said, this is going to be very specific to each of these. User data and concert data, this is going to be very high reads and very minimal writes, because for user data you're only writing when a person like makes a new account or if they change some of their user settings. Concert data, usually when a concert's is added to a system. It's not really changed. Sometimes they may add some seats or remove some seats, or if they're really toxic, change the seat prices. But yeah, ticket purchasing data, this will have more rights because people are consistently purchasing tickets. On a high level, it will still be having more, I would say it still has more reads than writes, but in terms of a ratio compared to these two, this one definitely has a higher amount of writes. And yeah, so typically, like, if a system has a high amount of reads, not that many writes, you say 100 to 1. If it has more writes but generally still more reads comparatively, then it would be like 10 to 1. Or let's say your system has a lot of writes, then you could say like 3 to 1. And then usually after you get you list all of this information, then you can kind of start doing database assignments, where basically you'd be like, okay, I think this database should be type A, this should be type B, etc. In Ticketmaster, most of these I would say would fall under like a SQL or NoSQL database. I don't remember off the top of my head, but I think if you do like the storage calculations, it's not a lot, and everything can really fit under a SQL database. But essentially all of these would be the same type. The reason why I did the Instagram one was I just wanted to show an example of a different type. So with Instagram, you'll have like Instagram posts metadata. So this is like captions, likes, comment, or like location, URL to photo, like the photo, etc. So this is all the metadata on the Instagram post. User data is another database, and then image data. So images are going to be a large amount of data, so we're going to want to put this in the S3 bucket, whereas these two maybe we would want to put in just like a SQL database or a NoSQL database. So in this example, like as you can see, there's a difference in the database assignments that we're making on some of them versus the others. And lastly, the last thing with databases and storages is you can also talk about database schema. This is not something required. If you feel comfortable with it, I would definitely ask the interviewer, being like, hey, I'm happy to dive deeper into database schema if you're interested. If not, I'm happy to talk about it later if we have more time towards the end of the interview. I think database schemas are definitely something that there are a lot of resources online and you can get really comfortable with, and I think that's really important because essentially, if there's a topic or an area that you feel stronger in, you can give these sort of recommendations to the interviewer and kind of steer them in a direction of topics that you are more comfortable with, allowing you to show off in those areas. But yeah, that's why I put it as optional, because sometimes interviewers, even if you're like they may not even want to talk about database schema, maybe they want to get to something else, which is why, yeah, it might just be optional. Alright, now it comes to API design. So in summary, you're going to have a bunch of requirements listed out, and even after narrowing it down, it's going to still be take a lot of time to be designing APIs for each one of these. I would definitely first ask the interviewer of all the functional requirements if there are specific ones they would want you to write API designs for. If they ask you for everything, that's fine. Like they're probably testing you to see how well you know APIs. But if not, they might just narrow it down to one or two, and then you can write APIs for that. Let's just do an example. So for Ticketmaster, let's say we are getting seat data for a concert. The first, what you want to list out is basically the type of HTTP request and then the URL. So I did like v1/concert/concert ID because we're trying to get all the seat data for a specific concert. So that's why it's important to put the concert ID in the parameter. The reason why I did v1 is because of backwards compatibility. This is not required, but it's just brownie points. But essentially having API version control so that if you have newer versions, your long-time users will still have the older versions of the API and their services won't just be completely messed up. Then you want to put in like what is being sent as a request. So access token, this is a pretty obvious one, and honestly you don't even have to say this unless security is a non-functional requirement, then you definitely want to say this, but I'm just listening here just in case. But yeah, your header is going to have an access token, and obviously we're sending a concert ID as a parameter. And the response back is we're getting a list of seats. This list will include data such as the specific seat ID, the type of seat, the price for the seat, and yeah, this will it'll just basically be sending back each of these data points for each seat. Yeah, this is basically like kind of the structure of each API that you want to be talking about. So just want to list out all the APIs in this sort of format, where you're basically giving like an idea of what this API function is trying to do, the actual request method and the URL, what is being sent in the request, and what is being returned in the response. One thing I wanted to touch on was if you were getting a list of let's say you're getting let's say you're doing you're designing an API for like a search where you're getting like a bunch of results. So in the Ticketmaster example, you're getting a list of all the concerts in your area. One thing you definitely can talk about is pagination. Not a requirement, but brownie points. Essentially, if you're not familiarized with pagination, definitely look it up. But yeah, you can talk about pagination, essentially how you want to incorporate an offset and a limit parameter into your URL. So on the first page, the offset will be set to 0, and then like limit could be set to like the screen size times 2. If they scroll down or maybe go to the next page, the offset will shift accordingly. And yeah, honestly, that's pretty much it. Then you get into the high level, which is where you have fun and you draw your Legos, kind of what we were doing here. Yep, this is kind of what we're doing here. Like I have some other ones. Oops. Yeah, like this is an example I'm gonna have in another video. But yeah, this is where you get your high level design, and then the last part is going to be the deep dive / bottleneck / single points of failure. So deep dive is they might want to like redirect your focus on specific areas. Maybe they want to talk about the databases, different replication patterns, different sharding patterns, etc. Maybe they want to talk about caching patterns, etc. And maybe they don't want to deep dive. They might just ask you, okay, what are some bottlenecks in your system, or what are some single points of failures? In which case you're going to talk about where you can improve the system. So for example, load balancer, having one load balancer is a single point of failure. Perhaps you can have a second one on standby in case the first one crashes. Message queue, having the data just saved in the message queue could be risky because if your message queue crashes, you lose all the data. You could have a database associated with the message queue. Anytime a data is added to your queue, it's also added to this database. Anytime it's pod from the queue, it's also pod from this database. That way, if your message queue crashes, your database will have all that information saved. Yeah, that is a quick example of that. And yeah, that's pretty much it with the outline. Those are the main steps. And that's really all I wanted to talk about in this video. I hope you guys found that helpful. If you guys have any questions or comments, feel free to leave them in the comments below. And yeah, thank you for listening.